So let me lay out the plan of today's class. Last time we started the perturbation theory. Actually, the full name is longer than just perturbation theory, but I will refrain from introducing the full name until we see the results. For a good physics theory, the results will tell us the validity. That is to say, when is the theory valid? And only then we will introduce the formal name of this perturbation theory. So let us recap what we had last time. First of all, we introduced the setting of a perturbation problem. The setting is that we have a problem that is hard to solve, characterized by the Hamiltonian H. To do any perturbation theory, we need some preparation on ourselves. We need to identify a big part of the problem that is exactly solvable. We call it H0, for which we know all the energy eigenvalues and all the energy eigenstates. Then we need to identify what is the perturbation term that we call H prime. So that is the first thing to do. Identify H0 and therefore know what is H prime. Last time we wrote down a formula, a very reasonable one, for the first order correction in the energy. Unlike the variational calculation, we are aiming at getting the first order correction to all eigenvalues. That is to say, pick any one in H0, the known one, and we want to know, under the influence of the perturbation part H prime, how will the H0 eigenvalue shift into something that could look like the eigenvalue of the full Hamiltonian H. We work it out for the first order in H prime by waving our hands. Our reason was, what else can it be? And then we work out a few examples that make sense, at least those results make sense. And then I introduced the way to connect our result to the big matrix formulation. The big matrix can be written down in the basis set of H0, and we know what the matrix elements are because we started out the whole course by writing the Schrodinger equation into a big matrix. And we found that the first order correction in energy is the simplest approximation of truncating the big matrix into one by one matrices. There's nothing simpler that you can do in truncation. You simply ignore all the off-diagonal elements, and that amounts to our guess on the first order perturbation result. So we are happy about that, but then there are several questions that remain. First, what is the first order correction in the eigenstates? Second, how about second order correction in the energy? Third, how could we derive these results formally, and at the same time, can we look at the formal derived results in terms of the big matrix? For example, we truncate it to one by one, only the diagonal thing, then we have the first order. Does it mean that if we look at 2 by 2 matrices out of this huge matrix, that will be second order? That makes sense, right? As a guess. And we will see how that comes out. Okay, so this is our plan today. So let me share the screen. So the first thing to do today is to set up a formal derivation of a perturbation theory. This is not only a topic in quantum mechanics. Okay, don't mistaken that as something belonging to quantum mechanics. No, it is a way to develop an approximation solution to an unknown problem when you know that a part of the problem can be solved exactly. That could happen in other subjects in physics, okay? So it is a mathematical subject as well. So let me start this very formal derivation. So this is our problem. Don't know how to do. We can identify a big part that is solvable exactly, and then immediately you know what is the perturbation term. By that we mean for this solvable part, we know all the energy eigenstates and the corresponding eigenvalues. For example, particle in a 1D box. Okay, so we know all this. So the starting point, the first step, actually that occurs in every way to do perturbation is to introduce an auxiliary parameter lambda at this point. Where does it go into? That is attached to h prime. So instead of h0 plus h prime, we write the problem as h0 plus lambda h prime. Of course, our actual problem refers to lambda equals 1. But for the moment, we would like to introduce the lambda to attach to h prime for several reasons. First of all, lambda helps us count. If we don't see lambda, that is called zeroth order. And that is the problem with h0 only. Or you can imagine when lambda is 0, then it is h0 problem, the problem that we know how to solve. So that is why we call it zeroth order. That has nothing to do with h prime. When we see one factor of lambda, then those terms are first order in the perturbation. Similarly, if we see lambda squared terms, then those are second order terms. Therefore, if you follow this formal method, later on, maybe some of you need to do research, do fourth order perturbation, at least you know what to do. Now, the mathematics can be tedious, but that is another matter, right? It is different from that you don't know what to do at all. So this is the first step, okay? Now, secondly, but very theoretically, if we are thinking about lambda is not big, say much less than 1, then we are very safe to do so-called order by order and stop at some order, okay? Now, you may complain, no, lambda is 1, not small, okay? Yes, in most problems that we encounter, the h prime itself is only a small effect, a small influence on the solvable problem. But mathematically, it may not always be the case. Therefore, we introduce the lambda to comfort ourselves so that we can claim, okay, we can keep lambda small and then all these results will work. And at the end, we can insert lambda equals 1, and that will recover the problem that we want to solve, okay? Now, these are formal statements. You will see in about 2 pages or so, lambda will drop out of the whole argument. It has accomplished its mission and then leave the scene, okay, gracefully. So let's see how it goes. With this motivation, we can write the eigenvalue that we are trying to find. This is the nth eigenvalue of the hard to solve problem, also in terms of powers of lambda. We have the 0th order, that is the known result, and then we start to get into the corrections due to h prime. We will write a lambda En first order. That is the term that we guessed the result last time. Okay, and then I illustrated with some tilted rail, things like that. Everything makes sense. Now, since this is first order, I attach a lambda to it. So illustrating that this is the first order to the correction due to h prime. Thereby, very naturally, we have a second order correction due to h prime. The thing that we want to derive is En second order, this one. To help us count, this is attached to lambda square. Okay? So if you want the third order term, you need to write another term here. Okay? But I will not do it for you because rarely do we need it in our level. Similarly, for the eigenstate, this is the unknown. We know all the 0th order eigenstate of the solvable problem. So this is lambda 0th order, lambda to the power 0. Now, we have a first order correction. Since it is first order, it is attached with 1 lambda, and lambda square, and so on. Okay? So we have a very systematic starting point. Okay? So guys, follow me. If you want to do perturbation theory, these are always the starting points. Okay? 得唔得啦？行不行啊？ Okay? So remember that is applicable also in classical physics problems, not only quantum physics problems. Okay? You may have a string, uniform density, but somewhere it's heavier. Then you can try perturbation as well. Okay? So our task is very humble. We want to derive first order correction in energy, first order correction in the eigenstate, and then second order correction in the energy. We will stop after getting these 3 things. Okay? We will not get the second order correction to the state because we don't need it. If we want the third order correction in energy, then we will need the second order correction in the state. Okay? So we will just shoot for 1, 2, 3. Okay? Rather humble. How to proceed? Well, we have no choice. That is the only equation we know. This is the Schrödinger equation. Okay? We want to solve this. So let's write out the Schrödinger equation. Left-hand side in lambda 0, lambda 1, lambda second power, lambda third power, and so on. Similarly, let's write out right-hand side in powers of lambda. 0th order, first order, second order, etc. Okay? So very clear in terms of the path to move forward. So left-hand side, h times psi. Okay? This is what we want to solve. The nth one, that can be anyone. all right? But we pick anyone to move forward, okay? That is an important point. So at this point, we ask, what is the correction to the nth eigenstate, all right? So now, the H is this, and the phi n order by order correction is that, okay? We only want to write out to second order because that will be sufficient for our purposes. Next, multiply out the terms. So do you see a zeroth order Hamiltonian multiply into a zeroth order state? That will be the zeroth order term. Okay, that's simple. Now let's inspect. How can we get a first power lambda term? We could have H prime multiplying into a zeroth order state. Okay, do you see? Lambda H prime psi n 0 will be a term with lambda. Okay, but there's another way. I could have a zeroth order Hamiltonian multiplying into a first order correction in the state. Do you see? H0 multiplying into lambda lambda psi n first correction. Okay, and you cannot find any other term that goes with single power of lambda. All right, so for this first order term, we have these two terms. Okay, this is a crucial step. Do you understand? Okay. Now let's be more ambitious. How about second order in the correction? Second order in H prime, basically. Okay. Lambda square term, so-called. Now, let's inspect. I could have H0 goes with second order correction in state, right? I could have H prime go with this. Then I will have lambda square. Okay? Therefore, I write down this term. Okay? Now, if you are not tired, but I am, so you can go on with a lambda cube term here or higher order term. Okay? That is the left-hand side. Then let's work out the right-hand side. All right? Now, the right-hand side, we already wrote down power by power of lambda, the En corrections. The first term is this, zeroth order plus first order plus second order, etc. The state has also been written as first correction, second order correction, etc. Okay, so the first line is trivial, just write down what we have written as power by power correction. Now, we can write down zeroth order term, first order term, second order terms. Lambda 0, that is, say, no lambda. There's only one term, this times that. Okay, so that is the zeroth order term. Nice. First order in lambda. I could pick this one, multiplying into low zeroth order in lambda. Okay, so this is one term. And then I could have zeroth order in energy multiplying into first order correction in the state. That will be another lambda term. Okay, so this is lambda outside with two terms. Okay, do you follow me? Same technique. Okay. Now we can also write down a lambda square term. All right. We have more choices here. We could have this 0th order in energy to 2nd order in the state, or 1st order in the energy multiplying into 1st order in the state here, okay? Or 2nd order in the energy multiplying into 0th order in the state, this one, okay? So therefore, unlike in the Hamiltonian side, we have 3 terms here. Okay? The reason is that on the left-hand side, the Hamiltonian always H prime stops here. H prime, we attach lambda to it to count. Okay? So up to here, do you understand? Know that? Okay? Okay? Now, if you understand, you are done with all the perturbation theories. Believe me, okay? You know what to do. Whatever order. That's it. Okay? We are done, basically. Now, the following argument is standard in perturbation theories. We have left-hand side equals right-hand side. That is to say, these two things equals. Okay? Get me? All right. So now they equal, that also means they are equal for arbitrary value of lambda. Well, you can think about it for arbitrary lambda between 0 to 1. But otherwise, lambda is arbitrary. Okay? Mathematically, it means that could not be accidental equal. Okay? That both sides cannot be accidentally equal. They may be equal for one particular value of lambda, but now I switch to the other one, then they cannot be equal, right? The only situation that left-hand side equal right-hand side for arbitrary values of lambda is that order by order, power by power of lambda, the coefficients are equal. Okay? Meaning, lambda 0 term, this must equal to that. Lambda to the power 1, left-hand side term equals right-hand side term separately. Lambda square term, this equal these 3 terms separately. Okay, do you follow this argument? This is the argument in the box. Okay, this is not mathematics, this is mathematical thinking. Okay? Okay? Now, with this, suddenly, we can write down the equations separately. Okay, we have 3 equations. Lambda to the 0, that is the 0th order term. We have that. Let's look at that. This is the solvable problem of the perturbation problem, right? Remember, H is H0 times H prime. We regard H0 is something that we know how to solve exactly. All right? Now, at least we recovered the 0th order problem by standard method. So this equation tells us nothing more. It just confirms, okay, you know the 0th order terms. Okay, this is just the unperturbed H0 problem regarding the nth eigenstate. Okay, in our context, we know this eigenstate, we know this eigenvalue, and we know much more. we know all the eigenstate, we know all the eigenvalue, okay? Nonetheless, it is very comforting to see this as a result of our systematic approach. The zeroth order problem means forget about H prime. You recover what you know, okay? Fine. The useful equations are the lambda to the power 1 term. So this one is our first order equation. And then we will have the second order equation. Okay? Now, if you go back a few pages and go through the whole process in your mind, it is not difficult. You just jump to this equation by writing down the first order term. It is again something like what else can it be, right? Zeroth order times first order correction. So behind the scene, there's a lambda, and then here there's a lambda attached to H prime. Here there's a lambda with the first order correction in energy, and then here there's a first order correction in the state with one single lambda, okay? So after you get used to this thing, you even don't need to go through the derivation in the previous pages. That's what I tried to convey. Similarly, we have the second order lambda square term, this longer equations. Again, you can immediately write it down if you know the setup, okay? We will always only get two terms on the left-hand side, okay? Because they're stopped with lambda H prime, right? And then there will be more terms on the right-hand side because both the eigenvalue and the eigenstate are power by power expanded, all right? So now, at this point, we have all the things. We will make use of this to obtain our two unknowns, okay? Identify our unknown. We want to get the first order correction in energy. We guess at the answer. We now want to confirm that our guess is correct. This is something we want to solve. Secondly, we want to solve for the first correction in energy that appear in two terms here. Psi and the first correction here and there, okay? So one equation inside which we have all the things we want to solve to first order. Okay, do you follow me? Miễn vui miễn phải mình tâm tất là. Okay. All right. So that is to say, if we are not too ambitious, we just want first order thing, this single equation suffix. Okay, we just play with this, we get all the answer. But if we want to do the second order correction in energy, we need this equation, and the only enemy here is this one, second order correction in energy. Okay, so we are done with all the necessary equations. Final remark, you see, when we write out these equations, lambda drop out of the consideration already, okay? It accomplished its mission, all right? We don't have lambda in it anymore. Of course, if you are very stubborn, you can say after we solve En1, we go back to the series and the correction is En0 plus lambda En1, and then at the end we put lambda equals 1. Okay, if you like it that way, fine. The result will be the same. So basically done. Okay. Then we have to extract results, order by order. So this is the first order equation. And I highlighted the two things that we want to solve, okay? And only after that, we have the ingredient because we need a first order correction in the state before we can get the second order correction in energy. All right, so we cannot jump order. We have to do it order by order, and it makes physical sense. Okay, don't show off your mathematics skills. Say I get second order, but I forget to get the first order. By physical sense, the first order correction in energy is more important than the second order. Only that when you see that the first order is not sufficient for your purpose, you want more accurate result, you go for second order. The first order term should be bigger than the second order term. All right? So that is, always keep some physical sense to guide you through the mathematical process. Okay, that is the way to do physics. Then we move on to collect results. Okay, so we will do something rather profound here. Now, let's look at this lambda to the first power equation. Okay, now you may wonder, we have two enemies in one equation. How can we do that, right? So I want the first order correction in energy as well as the first order correction in the state. Okay, but relax, don't worry. Plan for the strategy. Okay, again, this is a way to do physics. You don't blindly do mathematics. Okay, play with this and then write another line and write another line. You have to look for a strategy. Okay, how can I get this En first order? Okay, now obviously what you want to do is the following, right? At least I want to get rid of this zeroth order state that is multiplying. This is a function, but I want this number alone. Okay, I want to, how can I get rid of this n psi n0, the zeroth order eigenstate that I know? Okay, but I don't want it to be there. Think about it. Okay, I want En1 to be the single thing stand in the equation. Okay, now that's easy, isn't it? If I multiply the whole equation by this known eigenstate, this particular one n, known eigenstate for the H0 problem, integrate over all space, right? By normalization condition, I will get a 1. Thereby, this will stand alone. Okay, do you understand this strategy? Okay? We must do things for a purpose, all right? So, if we do that, suddenly we have our unknown stand out by itself. Therefore, we can put all the things to the other side and we are done, right? Okay, so let's do it. Okay, now pay attention, some magical thing happens. So the process is, we are interested in the nth correction to the nth state. That is your choice. You pick one to ask. The nth eigenvalue, how does it change to first order? Okay, you pick n, then I start doing things. You pick n, right? Then I multiplied the whole equation by the nth zeroth order eigenstate. That is something known. And then with a complex conjugate, multiply this every term of the equation. Okay? So let's do it. Here, first term. Here, second term on the left-hand side. Here, first term on right-hand side. Here, second term on the right-hand side. So I do that through the equation. Fair? That's why I keep the equal sign, right? Okay. Second, I integrate over all space. Okay. So I integrate everywhere, every term. All right. So that's equal. Okay. Very plain. Nothing fancy. Now, by the very fact that H0 is a solvable problem of a Hermitian Hamiltonian, because it's a real problem, okay, it's a real life problem, eigenvalues are real, we know that where is the enemy? E1. Okay, here. Okay, so we know that the right-hand side, okay, we pick up a normalization condition, that is 1, okay? So let's look at the right-hand side first. Immediately, I have this standalone, nice. And then the second term, this is a number, a real number, and therefore I will pick up this integration. Okay, that is the right-hand side. Nonetheless, I succeeded. Our unknown is now stand out. How about the left-hand side? Okay, I do the first term. All right, look at this. The first term, I multiplied it into the left-hand side, multiply into this known eigenstate. And this is Hermitian. Therefore, I can use the definition of Hermitian to interchange these two functions, okay? And this is equal to that. Now, this is an eigenstate of H0, therefore an eigenvalue comes out, all right? And it is real, it's a number, it gets out of the integral. So the first term on the equation, left-hand side, will give us a term with an eigenvalue, a number times an integral that we don't know what it is. Okay? But fortunately, this integral is exactly the second term that comes out from the second term of the right-hand side. Look at this. Okay? So we have a term on the left-hand side, cancels the term on the right-hand side, despite we don't know the first order correction in the state yet. That's the magical moment that I talked about. All right? Now, what is left is the second term on the left-hand side, this thing. Well, this thing is the expectation value of H prime with respect to the 0 for the state. An answer that we guess at, okay? So now, left-hand side equals right-hand side. Meaning, first order correction, this thing, equals this integral. Okay, because this term cancels the other term on the other side. Okay, so let me summarize. We obtained the first order correction term, which is the expectation value of H prime with respect to the 0 for the state. Okay, so that is the same as we guessed last time. So we have made the correct guess. By what else can it be? Okay, nice. That backed up my guess, the answer that I wrote down last time. Okay, nonetheless, we have got nothing new at this point, but we can also obtain the first order correction in the state. All right, now let's proceed. We need no new equations. We only need the same equation. We have conquered this one. We did this one. Okay, so this one is now known. Okay, and now we want the other unknown, this one. Okay, all right. So the strategy now is that, hey, let's get rid of this term. So the unknown will be left for us to solve. Okay, so this is a way to do it. All right. So now, how we can do that? Now, remember, nth, it's the state that you have chosen to ask the question. You want the correction on the nth state. But this is attached to the nth unperturbed eigenstate. But I have many other unperturbed eigenstates that I know for the H0 problem. What if the following? I pick any other one. As long as I don't pick the nth one, I'm multiplying into it by orthogonal condition. The integration will be 0, then I will make this term disappear from the equation. All right? So the strategy is as follows. I multiplied unperturbed state in, I call it the ith one, but I make sure that the ith one is not the nth one that you are asking the question. Okay? So the condition is I not equals to n. Okay? So let's do that. So I did that here. All right? So left-hand side, I have two terms. I have, look at the second term, okay? So you have the perturbation term. These are the zeroth order state. In principle, I can do this already, okay? Now let's look at the right-hand side. Our intention is to kill this term from the equation, okay? That's fine. We killed it because of orthogonal. It will not be here again. Let's look at the remaining term, okay? Now, the remaining term is troublesome, but it contains our enemy, okay? We want to solve the first order correction, all right? So now, we have this equation, okay? Let's take stock. We want this, and we want that, okay? Nonetheless, we are not worried about this term. In principle, all the ingredients are known. Just do the integration, okay? And the unknown appears here and there, all right? So we need to do some work. At this point, when you read the notes, go to the next page. So I stop here on this page, and then I need to jump to the other page and come back. Here's the physical conceptual argument. If there's no perturbation, H0 only, then I know the nth state eigenstate, psi n0. That is to say, if I include H prime, the perturbation, what we are going to do is the following. We want to get something like the correction here must be due to H prime, okay? But the point is that if H prime is not there, all the other eigenstate of H0 will have nothing to do with the eigenstate of the nth state. The reason is that they are orthogonal. By orthogonal mean one has nothing to do with the other, okay? And therefore, that motivated us the following procedure. When we need to consider the effect of H prime, the end result is we are trying to mix in the other eigenstate of H0 to form the new nth eigenstate. After all, it is a complete set. The x0 states are the complete set. Okay, so this line makes sense and is exact mathematically. The perturbed nth state can be written as an expansion of the complete set of the x0 eigenstate. And from here, we can construct the infinite by infinite matrix that we will go to later. Okay? But now we are doing perturbation. Let's keep it there. All right? So how to do it? We can single out an important term, right? In terms of perturbation, it means this is the dominating term, only corrections. So when you ask for the nth one, this nth one zeroth order will be the most important term. Nonetheless, there will be correction terms. Okay? So I single out a term and then I say there is the other corrections. Therefore, we have a goal. For lowest order correction to the state, we are thinking about the following. This is approximately 1, still the dominating one. So I write it as such. Then I'm going to look for this coefficient or to the first order in H prime. Okay? And that will be our first order correction to the state. So this whole sum together will be our lambda n1. Okay? So we have some way to look for lambda n1. In other words, we are replacing the task of finding this to finding all the coefficients am when m is not equal to the state that we are focusing on. Okay, so we want to find these coefficients. All right, so let us take a break and I will plug this back into the equation that we stop here. Then in a few lines, I can solve for the coefficients. And then we get the answer. Okay, so let's take a break and then we will resume in 10 minutes. All right.